Hello, everyone. Welcome to Foresight's Molecular Machines Group. Today, we're really excited to present this year's Feynman Prize Award ceremony. The Feynman Prizes were named in honor of physicist Richard Feynman. These prizes are granted by the Foresight Institute to recognize recent brilliant achievements in the field of nanotechnology. So this year, we have the honor of celebrating the accomplishments of our 2025 winner in the theory category, Nicola Marzari. So with that, I will pass the baton to you. Thank you so much, Nicola, for joining us.
Thank you. Great pleasure to be here. Very honored to receive a prize entitled after one of the great pioneers in science and in nanotechnology, and very happy to tell you a little bit about what is happening in research, and in particular in the research that I've been driving for many years now on, say, computational material discovery. I think you're seeing all the slides very well.
Yes, we can see the slides.
Okay, so let me get started here. And I decided to start from the conclusions. So at least you'll have these two take-home messages that I'll motivate during the talk. And one is that materials, as I always say, enable the technologies. And I'll give you example that really power our economies and sustain our society. So materials are really at the root of our own well-being. And we need materials, we need novel materials, we need better materials, more sustainable materials. And in this quest, I think the great advance that has happened in the last 10, 15 years is that we can join forces with, say, quantum mechanics, with theory, with algorithms. Of course, we leverage all the computational power that is being delivered, and in particular, machine learning and artificial intelligence, to really change our paradigm of discovery and innovation. And I'll give you an example, but I want first you to focus on the material side of things. And these are applications where progress in materials really changes what I call our societal well-being, and that goes from, say, the availability of energy to environment. Of course, a lot of, say, the US, Europe, and many other countries are what called high-tech and high-value societies, where the industry transforms materials into final products. And I'll give you an example. But, materials affect, say, healthcare, materials for health, pharmaceuticals, even understanding the stability of a, say, drug or the bioavailability of a drug is fundamental. And the list is very long, but what I wanted to give you is just maybe some practical examples. I take energy to begin with because we are all very familiar, and I like this graph that connects availability of electricity on the axis with the Human Development Index. Human Development Index to mortality, to childbirth, lactation, so to, say, women's education and so on. And you see this sort of broad trend following, say, availability of energy with human development. And in energy, it's very interesting also to remind everyone, we still rely a lot on oil, on natural gas, on coal. I always like to put numbers that are understandable. So the world uses whatever 600 exajoules, but maybe it's good to remember 12 barrels per person per year. And the consumption is, say, steady, is actually decreasing for oil. Renewables have been increasing, things like solar and wind. And of course, every day is in the news, whatever is the geopolitics of oil and oil reserves. This comes from British Petroleum and listing the countries that have the most reserves. And there is a lot of, say, push around the world. Maybe it's more relevant these days in Europe for, say, clean energies, but even clean energies from, say, solar to often relies on materials and minerals that are actually not so clean. Lithium-ion batteries require cobalt, require lithium. Of course, electrification requires a lot of copper. So there are a lot of, say, challenges in actually deploying even optimal solutions. I give you the example of energy, but I want to give you maybe more practical examples. I guess you probably recognize Steve Jobs here, but what happened with the iPhone and smartphone was actually made possible by the existence, discovery, and actually sort of translation into industrial use of materials like transparent conductors. So you see, we could move away from the keyboards to using the finger as a pointer, not only because somehow someone idea that the finger was a better pointer, but because all of a sudden we could produce high resolution display that were coated with conductive materials that were transparent. And conducting and transparent don't go well together. So that's why there are so few materials that are possible. And we have high energy density lithium-ion batteries that were based actually on polymers, so somehow could be squished inside the form factor of the telephone. And I guess everyone is familiar with smartphone. Probably fewer people are familiar with Clara Fritz Haber, but this is, I think, a story that has changed the last 100 years. And Fritz Haber was a German chemist, and he did things that were absolutely essential for our survival and things that were not so nice. And I think he's also introduced the way, say, materials have two uses. He was actually very fond of chemical weapons, so he was actually involved in deploying during the World War chemical weapon on the Eastern Front. And Clara, his wife, that was actually the first woman PhD in chemistry in Germany, killed herself in protest of, say, his engagement. But we should all be very grateful to Fritz Haber because he, say, discovered, I would say, the most important material of the 20th century, and this is the iron-based catalyst that allows to transform nitrogen, the N2 molecule that in the air, into ammonia through the Haber-Bosch process. And ammonia is the fundamental component of fertilizer. We wouldn't be able basically to produce food for more than 8 billion people without fertilizers. Often we say that Fritz Haber saved more than 1 billion people from starvation. And of course, ammonia is also what need to do explosives. So all the bombs of Second World War were actually produced thanks to that. And so this is a very interesting example. A few other examples of, say, how materials transform society. Of course, we have jet engines and very efficient jet engines because we have materials in the blades that can sustain the temperature of the combustion chamber. And actually, if you are a nervous flyer, it might be good for you to know that the melting temperature of these blades, these nickel superalloys that you see here, is actually around 200 degrees, 200 Celsius, lower than the temperature of the combustion chamber. So basically the jet engines should melt like butter, and the only reason why they don't is that they are coated with this very thin layer of certain oxides, thermal barrier coatings, that actually are able to screen the inside of the blade from this temperature, and the temperature drops by 200 Celsius in just a fraction of Another example that I like a lot, I think both myself and Marco Fornari were involved in some of this research. There has been a push for decades, especially from the US Navy, to find better piezoelectric materials that transform, say, pressure into a voltage difference. And I think a revolution in this took place in the late 90s, where new, say, lead zirconate alloys were discovered. And these days, like the Virginia-class submarines, are actually covered in this super high sensitivity piezoelectrics that are the same one that we use to do the three-dimensional ultrasound that you might have often seen, and that is able to visualize with great detail and three-dimensional precision what is going on. So this was just a bird's-eye view on how, say, materials influence technology and affect society. And I like to cite an article from 2019 that was really predicting the future, and it was focusing on what could be the new technologies that create $1 trillion markets. And what Barnes in 2019 wrote about genetic engineering, Cas9, artificial intelligence, you all see, but also new materials. They talked about a materials revolution where simulation techniques, computing power, and machine learning are enabling researchers to automate much of the discovery process, accelerating the development of new materials. And this is exactly what is happening now. Of course, what helps a lot is that anything that is related with simulation, with machine learning, with AI uses computers, and computers have been increasing amazingly. I always say when I started doing research in 1993, I could take an example that a calculation that would have taken a year then It would take 1 second, actually. This was from 25 when it took 3 seconds, and now it takes 1 second, a 30 million fold increase. I actually gave once a talk at the, say, Wall Street billionaires, and so I told them 100% returns every 16 to 18 months, and they were very happy about hearing this. And so I would say this computational power and computational science is really changing the way we do scientific discovery. Probably many of you have never heard about the density functional theory, that is the power horse for a lot of what is done in materials. But what is interesting is that actually is the most scientific discipline in the entire scientific medical engineering literature in the last 200 years. So you would have thought that maybe the most cited papers relate to cancer. They relate, I show here Watson and Crick and the discovery of the structure of DNA. But in reality, the sort of most represented discipline is one that very few people know. And it's about, say, using quantum mechanics to predict the properties of molecules and materials. And these days, it's not only academia that is doing this. Actually, somehow interesting, refreshing seeing major companies say, I show example from Nature papers of Microsoft or Meta working on catalysis, Microsoft, you see, working on discovering the properties of novel materials, deep learning, Google and DeepMind, say, is publishing again in Nature on millions of new materials discovered with deep learning. And it's not only the big companies. There was a very interesting paper just last month in MIT Technology Review highlighting some of the material startup that came out in the last 1-2 years. And you see the money raised 100 millions in September, $350 million in October. So this is really major investment in companies that use simulation, artificial intelligence, machine learning to discover novel. And so why is this possible and what is that we can predict? I often show this picture because I think it gives you in a very immediate way the sense of what can be done. And this is, I'm actually based in Switzerland. This was a project with the Swiss watch industry making gold in a novel and fascinating colors. And so we had a project with them in predicting the color of metals. Of course, you can take a piece of gold, you can measure accurately with an experiment the color of gold. But if you want to discover maybe a novel gold alloy, a novel gold intermetallic, you need to produce it and measure it. And you can do it once, twice, you can do 50 times. But if you have to do it thousands and thousands of times, it scales with your, say, workforce. So if you want to double the number of combinations that you want to explore, either you take twice the time or you just hire twice as many people, but you have also to double your laboratory size. Instead, once you build a field algorithm, a computer code, and even a machine learning model of what should be the reflectivity, the brilliance, the color of a metal, and when that becomes accurate, and this is exactly what we did. You see in top panel, I just showed 3 examples of interestingly colored metals or metal compounds, but once you're able to predict the color and you see how well it can be predicted because what is done on top doesn't have an experimental input, then you can change completely your discovery pipeline. You don't do experiments, you do simulation and you do simulation and you do simulations until you find something interesting, and that on that something interesting you do an experiment. And you can do this for the watch industry. You can do it from nanotechnology. This is maybe more technical, but say comparing the resistivity of a single layer of graphene, what can be done in experiments on the right, and what theory can predict using a very complex state-of-the-art quantum mechanics. And basically, it's as good or often even better than the experiment. And this is a case of, say, nanotechnology. This is a case of looking at the evolution of, say, what happens at the surface of a material as it starts melting at a resolution, at a speed for which we don't actually have experimental capabilities. So here we understand how little islands of the material start melting and coalescing, and you wouldn't even be able to do an experiment to follow this. You might see the really atomic timescales, the little atoms vibrating and moving at a speed that cannot be monitored. Some of the properties that can be seen with experiments are actually the vibrations of molecules during chemical reactions. And so on the left, you see an experiment measuring vibrational frequency, but not knowing actually what those vibrational frequencies correspond. And the simulations on the right actually can connect an experiment with a microscopic picture, because one can explore all the molecules and all the possibilities and tell what should be those vibrational frequency and match them back up into the experimental data. And so now our, say, chemistry colleagues understand that as you change and scan potential in your chemical reaction, some chemical reaction take place, that they disappear, some other appear, and so on and so forth. And to conclude, I go from, say, maybe developing novel material for batteries, where actually one these days can use machine learning to teach machine learning models, lithium-ion in solid state batteries, and one could also learn what would be the better composition of those batteries. We were working here, now this is public, with a company, with Solvay, that has a certain compounds for the solid state batteries, and they wanted to optimize the speed with which lithium goes back and forth from the cathode to the anode. So we were able to find what elements we should dope this battery with. And in particular, you see earth abundant materials like chlorine and magnesium, but also what is the best combination of the two to have optimal conductivity. And only after we did all of this, we identified among thousands of possibilities the couple of dopants and co-dopants that were optimal, and their composition. Our experimental colleagues synthesized the materials, made the material, and saw that they were performing much better than what they had, and so went on patenting and bringing this to the market. And I'll conclude this part, and now maybe I just show one or in-depth example with a little bit of a puzzle that no one has yet been able to solve. And this is, I like it because it's very easy to understand. We can take all the materials that we know. I'll show you later how many materials do we know, but this would be, say, the silicon in our computer, the lithium-ion battery, the photovoltaic, the metal alloy, and so on. And actually there is a regularity in the number of atoms that are periodically repeated that is slightly mysterious. So if we were to study silicon, every, say, physicist, material scientist, chemist know that the microscopic structure of silicon is given by two atoms periodically repeated. You look at some other material, you might look at one of those ferroelectric and piezoelectric materials for the sonar and for the ultrasound, like barium titanate. We know that those have 5 atoms that are periodically repeated. And so we can classify all materials in the world in terms of what we call the primitive cell. How many atoms are periodically repeated? What happens, you would think that is very easy to understand why, but what happens is that there is a pink histogram on the left here of primitive cells that contain a number of atoms that is a multiple of 4, and no one still understands that. So this is, I guess, a good puzzle if you don't know what to do during your weekends. So let me just show you now a couple of in-depth examples, and then we'll wrap it up. Now, if you come from pharma, if you come from molecules, if you come from chemistry, you probably know that we have made and we are able to make millions of compounds. But when rather than having a molecule, we need to have something solid, 3-dimensional bulk materials, actually we have much fewer candidates. Actually, what we have been doing in the last 10 years has been harvesting the entire scientific literature, again, everything that has been published. And the interesting results is that the core unique materials, the silicon, the germanium, the diamond, the barium titanate, the gallium arsenide, and so on, are not that many. Mankind has only discovered up to now 72,000, and this list grows every year, but less than 100,000 materials. So not that many, and many of us in the US from the Materials Project to Waveflow to OQMD, or here based in Europe, the Materials Cloud, we actually expose to the scientific community all these materials because a lot of efforts that companies that I discussed before, the academic groups, do are searching interesting properties for these materials or trying to invent novel materials that have never been studied, but they should be existing, they could be made, and they could have interesting properties. Since Feynman and nanotechnology is behind us, I'll give you a fun example that has actually been very successful and very much used. So we have this now database of 72,000 materials, and what can we do with this? And one of our first projects in this field was a scotch taping material. Some of you might be familiar with graphene, the idea that you could take a very boring piece of graphite, is what is used in the pencils, the lead, and actually with very elementary technology, with scotch tape, if you had delicate hands, you could actually exfoliate a single layer of graphite, what is called graphene. That is really one of the poster children of nanotechnology, got the Nobel Prize in 2010, and that was only 5 years after the discovery by Gaiman Novoselov that one could be exfoliated and that the properties are incredibly interesting. And so what did we do? We said, well, we have these 72,000 materials. Let's scotch tape all of them. Now you can understand right away that if you wanted to do it in real life, you would first need to make sure that you are able to make this 72,000 material, and then you would need to have 72,000 PhD students painstakingly scotch taping every one of them and then measuring their properties. But rather than doing it in real life, we could do it on the computer. We could look at this database, try to look at all the materials that seemed promising, that they were composed, that you see, by two-dimensional sheets that we could exfoliate, and then we set up a pipeline for automatically identifying a promising material and really calculating with quantum mechanics many properties starting from the binding energy sheets, how difficult it was to exfoliate. And once you set up the algorithm for one material, you just have to run it 72,000 times, and so you can just let the computer do all the work, pick an entry from the database, and do everything that is needed. And you see, it's all sort of recorded, persisted, and kept track to calculate the interesting electronic, optical, magnetic properties, the vibrational, thermodynamical properties, but in particular the binding energies. And happily, the computers still don't get tired, so I always say we can let the calculation for weeks and we can all go scuba diving and come back and see what the computer has found. And as I told you, this project was a lot of fun, and because all of a sudden we found, well, at the beginning a couple of thousand, and now we have basically 3,000 materials that they can all be exfoliated, they can all be scotch taped into monolayers. And what can you do with this monolayer becomes very much the domain of, say, future information and communication technology. I won't go too much into the details of this, fairly complicated, but one of the materials that we're looking for were so-called topological insulator, quantum spinol insulator. This is again a recent Nobel Prize, 2016, the Coster. But the beauty of this is that, again, we could systematically go through those 2,000-3,000 materials and calculate the electrical property, and we found something absolutely unexpected, for which there is a little story that is a lot of fun. There was, in 2008, an expedition of a group of mineralogists from actually Czechoslovakia that were exploring the iron mine in Brazil, close to Belo Horizonte, what is called the Rifero, and they found a new mineral, a new platinum mercury compound. They recorded it. They were able to sort of also synthesize it, and they published this discovery in a scientific journal in the Canadian Mineralogist. And I don't know how many Canadians there are in the audience now, how many mineralogists are in the audience. I would say the number of people reading this journal is actually very limited. But our computers don't get bored, read that journal, and this novel mineral discovered in 2008 that is called Putting made it calculations. This is again from those papers, the discovery in the left, in the natural state, and the synthetic pingite that was made. And the beauty of Gate is that it looks a lot like a graphene. It's an hexagonal, say, pattern, not of carbon, but of mercury. And for the first time, this was what is called a Cain-Meili quantum spinol insulator. So everyone got extremely excited about the electronic properties of this material. And so our colleagues in Geneva ran and replicated the synthesis route that was made by the authors in that Canadian mineralogist paper. They made what we consider a very good sample of these materials. If you look at it in an STM image, you see the perfect hexagonal. And then they measure the properties, and these are measured in synchrotron. This is what is called the band structure ARP. And where you see ARPs here, it's actually the result of an experiment. And what you see called the DFT is the result of our calculations, and it really matches extremely well, and what we predicted is what they found. So this is an example of really going all the way through from a database to a novel material with novel properties that then can be made. And again, in the spirit of nanotechnology, I'll tell you a little bit of what is, in my opinion, or what will be a new frontier. And it's not even two-dimensional materials, it's one-dimensional material. Is atomic wires that often can be made by synthesizing 3D materials that, when looked at the atomic scale, actually look like wires sort of kept together by very weak, we call them van der Waals forces. And again, we have found more than 800 known materials that could be exfoliated. And actually here you might see here this very thin atomic wire. This is going to be the thinnest metallic conductor that we will ever be able to make. This material that is made by copper and carbon is extremely strong, is extremely resistant to oxidation at variance with many of the materials that we use now for wire interconnected in computer chips, and it conducts electricity extremely well. So there will be a lot in the next future, I think, of one-dimensional material. Let me maybe sort of wrap down this talk. I don't want to bore you. You've seen example of, say, looking at two-dimensional materials, looking at one-dimensional material, but of course, bulk three-dimensional materials are also very important. And one of the things that we must, with, say, completeness, the electronic and optical properties of materials. This is what we do is a bit technical, or we are able to encode it. But the very nice thing is that for any materials, we are able to understand what the electrons do, and the behavior of electron, the behavior of the electronic bands can be at the core of materials that we would really want to be performing better. One example is thermoelectrics, that are materials that, say, can transform heat in electricity, and so they are able to recycle waste heat and convert it into electricity. Or they could, if we could improve their performance, substitute refrigerators, because they would be able to cool down, say, whatever we want, starting from the food in our fridges, much more efficiently. But in order to be a very good thermoelectric, we need to understand very fine details of the electrons, and it's very difficult to have intuition. So these days it's much better to calculate what electrons should be doing, and then identify the materials that are most promising. So thermoelectrics is one example. Another example that I like a lot is making sandwiches of this. I guess are some sophisticated Chinese multi-layer sweets. But what happens is that these days we are able to grow one material on top of another, and if we choose the right combination of materials, this is in the real world between titanium aluminate and strontium titanate. You see, this is a real image of a very sharp interface between the whitish looking material and the darker material at the atomic scale. And if you choose materials that are lattice matched and have the right difference, some of the polarization of the electrons, you're able to create a perfect, again, two-dimensional, in this case, electron gas. And again, these are technologies that are super important to try and move around in computer chips. And right now we only know one example, but with our computational exploration, and now we have hundreds of examples where this two-dimensional electron gas forms at the interfaces of materials that are lattice matched. And if we control and understand what electrons do, there are many other properties I don't want to bore you, but like we can be looking for novel superconductors, or materials that conduct electricity without any activity. And this was very recent. We have almost double the number of possible superconductors. And I'll conclude, I think, and this was maybe the motivation of the prize, the beauty of what we are doing these days is that we can make these capabilities available to the entire scientific and industrial community because, say, a variant with, say, experimental facility, simulation capabilities can be shared. And so I've mentioned it already. We expose on what we call the materials cloud, all these materials and all their properties, but we also detail on how all these properties were calculated so people can explore this statistical graphs that can trace every step in the calculation. But maybe most importantly, exactly as we are able to do automated calculation for ourselves to explore material space, we can give those automated capabilities to the communities. And it's really the equivalent of extremely sophisticated experimental facility. We give a computational facility that are able to predict many complex properties. And this is just an example on how these capabilities deployed on some of the large-scale experimental laboratories where, say, an experimental scientist can sit in front of his, say, desktop, and they can probe all the materials databases in the world, trying to find one that is of interest, and then that person can calculate property from, you see here, the spectroscopic properties that are necessary to understand what are those molecules at the surface, what we call infrared spectra. These are more complex, say, example of what happens when you probe the structure, the magnetic structure of a material with neutrons. This is what you do, say, X-ray spectroscopy and in XPS, or this is what you do when you use muons to understand the structure and the defects in the materials. So all these capabilities, rather than requiring tens of millions of dollars of investment for every experimental facility, can just be run out of a desk. So let me wrap it up. If you have been interested or fascinated by this, I try to put everything that I know in these 13 pages. Is a review of nature materials that you can just go and download and read if you're fascinated by this world. I want also to thank all my students, a little bit scattered between Lausanne, Zurich, and Bremen, and soon from December also Cambridge. Thank all the different, say, entities that have funded us, starting from, say, my career at MIT for many years and then moving back to Europe, and also, as you can see, a lot of companies doing this. And I'll just leave you with my favorite cartoon from the New Yorker that says things were done very differently on the farm when I was your age. And I thank you all for being here and very happy to engage in discussion or any questions that you might have. Thanks a lot.
Thank you, Nicola, so much for the deep dive on your work, and congratulations again on the prize. The way that we can move into this Q&A, since there are no questions in the chat, I invite you, members of the audience, to raise your Zoom hands, and that way we can coordinate questions for the Q&A. Tad.
Hi, thanks for this talk. Interesting, sir. One of the things that I was wondering that you didn't maybe get a chance to mention is the thing of doing simulations of large molecules, large structures. They can have several low energy states with similar energies. So if you're trying to find, say, the ground state, you need to be fairly accurate in your simulations. And so I was wondering, in your simulations for studying the properties of these different materials, how much is accuracy a limitation on the material material discovery that you described.
Yeah, no, that's an incredibly good point, and it's one of my pet peeves. I always talk about predictive accuracy. We need to be, let's say, accurate enough that what we do is meaningful to motivate our colleagues to actually make the molecule and the material. Interestingly, the most boring properties are the most difficult to predict. So understanding if a material is stable is incredibly tough. If you want to know if barium titanate wants to be barium titanate, you need to compare its energy with all the other possibilities. Barium as a metal, titanium dioxide, barium oxide, and so on and so forth. You need to take into account the effects of temperature, the vibrations, and so on. Room temperature on the energy scale of atoms of electron is extremely tiny for people that are used to these units. It's 1/40th of an electron volt, where binding energy hundreds of times higher. So predicting, say, the stability of a material is tough, and even tougher is predicting the conformation of floppy molecules. That's why, say, protein folding has been such a challenging problem. And at the end, a lot of great progress has happened when DeepMind with AlphaFold showed that it was better to machine learn from what had been measured experimentally than trying to use simulations. So that's also why we are not to predict novel materials. We work with known materials because we know that they were made, and what we focus is on how accurate we are on predicting the properties that we want to measure: the resistivity, the conductivity, the superconductivity, the color, and so on. And there are easy properties and there are difficult properties, and so it really depends. Everything that I shown you were examples of properties where we have a good handle. That is, if we say that a material is superconductor with a temperature of 39 Kelvin, it might be that you do the experiment, it's 45 Kelvin, it's 35 Kelvin, but we are in the right ballpark that is good enough to then go into the technology of this. But the accuracy is really property dependent, and there is not a generalizations that one can make, and there are a lot of things that we can just not predict well enough.
Great. Next up, we have Marco.
Thank you. And I have two questions, Nicola. The first one is on the frontier that you discussed, and you discussed the frontier from a technological perspective in terms of dimensionality, right? Lower the dimensionality and explore new situation, new effects at lower dimensionality. So there is a space to explore other frontier, like a non-equilibrium system or system that are stable at very high temperature or very high pressure, but can be somehow morphed and used in different environmental situations. Or, on the other side, in the spirit of the Feynman, right, doing metamaterials that are really engineered from a structural point of view. I would like to know your about this aspect. And another related question is that instead of thinking to the technology, can you say what really the field have advanced from a fundamental scientific point of view? Or I'm thinking to and providing a new way to interpret quantum mechanics. Did the field of material ever done something like that?
Yeah. So let me start with the first. I would say you brought two examples. Metamaterials is extremely relevant both for science and for technology. So metamaterials is a name where if you want the architecture of different building blocks with different capabilities give rise to a physical properties that is very important. Let me give you an example that comes from my time at MIT when, John Johnopoulos and Ned Thomas and Joel Fink really sat down as good theorists and thought at making a material that could reflect light at every possible wavelength without any loss. Now, a metal mirror can reflect 99.9% of the light, but only a certain wavelength, and there is a bit of a loss. And they used a concept from electrons in periodic systems, but they applied to light in periodic system, and they figure out that if create what they called a dielectric mirror, so material made by one sheet of plastic and then another sheet of plastic and then another sheet of plastic, and with the right thickness and with the light dielectric constant, they could actually make sure that it was a perfect omnidirectional. And you would say, well, why is this important? Well, this is important because they learned to do that not only with a flat mirror, but with an optical fiber. And so they were able to make now optical fibers with maybe 40, 50 layers of different plastics that they were able to bend light. And why do you want to bend light? Well, in their case, they wanted to bend laser light with plastic, and all of a sudden we had the technology to go into hospitals and now do operation, like if you have to do, say, an operation on your throats, on your larynx, on your vocal cords. You used to have to cut a hole here and go with a laser. And now instead with this optical fiber, they can go and they can bend the laser, and it becomes all of a sudden non-invasive surgery. So I think metamaterials, and there are a lot of examples from invisibility cloaks to optics to actually materials that have mechanical properties that we would have never imagined, that they can absorb very large amounts of, say, elastic energy in a collision. So metamaterials are extremely useful. Dynamic-driven materials are still more in the sort of realm of very interesting and fascinating science, not yet a technology, but there are very interesting way of thinking at, say, materials that change their properties because they are periodically driven. There aren't technologies, but there is a lot of science. Now, this was for your first question. For your second question, had we advanced science, had we advanced quantum mechanics, are we sort of going deeper because of materials? I think there are two directions. One is that materials have enabled detectors that wouldn't have been possible, starting from some of the very, very high magnetic fields that you have for what is called NMR, say, colliders. But I think maybe an example that everyone will resonate is quantum computers. We still don't know what quantum computers are useful for, at least in my opinion, but they are some of the most fascinating pieces of applied science where we needed to do, depending on what is your quantum computer, transmon, superconducting qubits, semiconductor qubits, cold ion. It's really a world where the most advanced science tries to do something that pushes what we understand about quantum mechanics, but ultimately to deliver computational technology that we would like to be, at least probably for very narrow fields, better than anything else that we have.
Thank you. I think we have time for one, maybe two more questions. If there is anyone else out there with something to ask, comment also. And if not, then we will conclude our prize ceremony.
Great. Thanks a lot. Very honored and a great pleasure. And I think the reaction, let's see, it doesn't send the fireworks, but thank you all. Really being a great pleasure to be here.